We now want to study the relation between the number of large and the number of small angles in a face. And if we count those, then for the interior faces, we will find that we always have two small angles more than large angles, and on the outer face that we have two large angles more than small angles. We will only prove this for interior faces. For the outer face it's analogous. And we will do this by induction on the number of large angles we have. So let's say that a face has 0 large angles. Then by this lemma it must have exactly 2 small angles, and this is clearly the case if we just move along the right side and the left side. Then we only go up, we only get small angles. If we have more sources or sinks here, then at some point we have to go down and we must have a large angle there. So here it's easy to see. Now let's assume that we proved it for some L of f and we want to show it for something larger. We want to split the face with an edge from a large angle at a low sink hue to some other vertex. A low sink for us is one like this that lies at the bottom. You have a large angle above it. So what can we split it with? We don't know what the other vertices here are, so we have to go through all the cases. It can be a sink or a source with small or large angle, or it can be neither of those. Let's start with a sink with small angle. So we take our face and we add another edge here in between. That splits the face into two smaller ones, f1 and f2. And by induction this formula holds for f1 and for f2. Now let's count. How many large and small angles do we have here compared to f1 and f2? This large angle here gets split, and in f1 and f2 it doesn't exist. So the number of large angles in f1 and f2 is exactly 1 less than the number of large angles in f. The small angle here gets split. It's a small angle in both f1 and f2. So the number of small angles in f1 and f2 is 1 larger than for our face f. And by induction, now this one here is a minus 2, and this one here is a minus 2. Now we add 1, we have here minus 1, so we add another 1, and then we get minus 2. So for this case it works out nicely. What if V is a large angle? Again, we split it by adding this edge. Can you figure it out now? Oh, it's the same. This large angle gets split. It's neither small nor large here, so the number of large angles goes down by 1. But this large angle still exists in f1, while it's a small angle in f2. So we created a new small angle, so here we have 1 more. And then again we get to a minus 2. Don't get confused with the pluses and minuses here. If we have 1 less large angle in f1 and f2, then we must have large angles of f1 plus large angles of f2 plus 1 to get to L of f. That's why I always say we have fewer large angles here, but we have a plus here. Let's go through the other cases. Let's say we don't have any of these, then we try to match it with a source. First, a source with a small angle. So we have our u here, our v here. How can we add an edge? Here we see that this is actually not possible. So we cannot do that. What if we have a source with a large angle? Well, then we can split it here. We again get two faces f1 and f2, and both these large angles don't exist here. So the number of large angles decreases by 2, and the number of small angles, those don't become small, is exactly the same. Again, we use induction here, and we get a 2. What if we don't have any of this, so we only have a vertex that is neither a source nor a sink? Well, again, this large angle here gets split, and we create a new small angle. So the number of large angles goes down by 1, and the number of small angles goes up by 1. And again, by induction, we get a -2. And if we don't have a low sink, then we must have a high source, because those are the only ones where we can have large angles. We want to summarize our findings in a lemma. In every upper planar drawing of G, it holds that for every vertex, the number of large angles is 0 if it's an inner vertex, and 1 if it's a global source or sink. And for every face, the number of large angles we have is the number of sources, the number of locus sources minus 1 for interior faces, and the number of locus sources plus 1 for the outer face. This we can easily see on some examples. We have one large angle here, but 2 sources. We have one large angle here, but 2 sources. But in general, it follows just from the 2 lemmas we had before. In lemma 1, the number of large plus small angles is 2 times A of f. By lemma 2, number of large minus small is plus minus 2. So just add this up, we get 2 times the number of large angles is 2 times the number of sources plus minus 2, and then divide the whole thing by 2, we get exactly this. So now we know for every face how many large angles we must have there. But still, we have to assign from the vertices to the faces where the large angle is. And for that, we want to define a consistent assignment. Well, let's say S and T are our global sources and sinks. Then a consistent assignment is a function that maps all the sources and all the sinks to the faces, such that V is mapped to an incident face, where V will then form a large angle, such that to every face we assign exactly L of f, which we can compute from the number of locus sources and sinks by lemma 3. Let's have a look at an example. We have this graph here, and we have some global sources and global sinks. For every face, we can calculate how many locus sources do we have. For example, here it's 3, it's this one, and this one. From this, we can easily calculate how many large angles must we have there. That's just one less for the interior and one more for the outer face. And now we want to assign the global sources and sinks to the faces, such that to every face we assign exactly as many vertices as we need large angles. And this here should look familiar to you. We have some vertices, we have some faces, and we want to have some angle assignments. That's almost the same as we had in the orthogonal drawings. There we also wanted to go from vertices to faces, but also from faces to faces. And here we can actually solve it almost the same way, via a flow network. So we want to have a flow of 1 between a global source or sink and a face if the face gets the large angle of this global source or sink. So we can build a flow network. And the vertices in this flow network, that's exactly the global sources and sinks and the faces. The edges in this flow network are edges only between vertices and faces, and those are defined by the incidence. So a vertex is connected to a face if the vertex is incident to the face. The lower bound for all these edges is a 0, and the upper bound is a 1. And the production for all of these vertices is 1 if it is a global source or sink. Those want to give one large angle away to a face. And for the faces, what is it? It's exactly this number of large angles that it wants, that we can calculate by minus number of locus sources minus 1. Now in this example, this face here has 1 locus source, so it gets a 0. This face here has 3 locus sources, here, here, and here, so it gets a minus 2. This one has two local sources, these two, so it gets a -1. And on the outer face, instead of removing one, we add one, and then it gets a -3 because we have 1, 2 local sources. And then we can just solve this flow network and find some valid flow that gives us a consistent assignment. We don't even need a cost function, we just want to find any valid flow where all the productions and demands are met. And that assignment might look like this. Every global source and vertex gives one angle away. This gets two large angles, this 1, this 0, and this 3. And a drawing that realizes this consistent assignment could look like this. We have from this vertex to this face the large angle, from the outer ones to the outer face, and from the two orange ones to this face. But even if we switch it up, let's say this vertex should now give the large angle here, and this the large angle here, it's still possible to draw it in some way that we can get a drawing of this consistent assignment. And how to get such a drawing, that's what we want to do in the final part.